me start the recording here. Fun with invariance? Not yet? Well, just in case any questions come up next week, I have updated the website to show that I'm going to be having office hours. So while I would normally be teaching, since I'm not teaching in finals week, 12:30 to 4:45 on Tuesday and Thursday. I'm just going to sit here with my Zoom open, and if you want to come by and ask me a question, or if you want to come log in and do work and sit here and work on it and pop in and out with questions, that's fine too. We have one question in the chat window. How do we know which model is the one we compare fit to? I think sometimes we compare to baseline configural and others do not. Great question. So the logic of this is the same as what was demonstrated in the invariance examples, where section 1 is a configural model. So that means that everything is estimated separately except for the parameters constrained to identify the factor in each group. Section 2 then is metric invariance, and so metric is always compared back to configural, and you're looking to see at what point you can constrain as many loadings as possible and have the model fit not worse than configural. For section 3, it says use your last metric invariance model to examine scalar invariance. And so wherever you left off with in terms of which loadings can be constrained and which ones can't, that is then your new baseline for comparing section 3. And so it says also examine scalar invariance for all intercepts of the indicators for which metric invariance held. That means if any of the items did not have their loadings constrained at the end of section 2, their intercepts do not get tested. They get kicked out of the tournament. And so then the last good metric model is the comparison for scalar. And then in section 4, we're switching over to IFA. So starting over again with configural. Configural is then the baseline for section 5, which is the metric model. And then you carry forward your last best metric model, whichever loadings could be constrained, to test thresholds. And we're not dealing with residual variances for either of these, I believe. Let me see that. So, did that answer the first question about baselines? Okay. And let's see, other questions. Can I release several constraints for the intercept at the same time? I would not recommend doing that. Even though it's tedious to do them one at a time, it's hard to anticipate what the net result of the other parameters would be after you change the ones that are problematic. So it's one at a time is the practice that I would like you to get with this, and that's what I would generally do in life anyway. Other question about constraining loadings. When you constrain a loading, do you also have to constrain that item's intercept? I think I was running into something weird with that one. Not at the same time. So when you're testing metric invariance, you are constraining loadings only, and because you're constraining loadings, you would release the factor variance in the non-reference group so that it can be estimated. At that point, you leave the intercepts and the factor means alone, you don't touch them. Once you get into the scalar stage, you would keep whatever loading constraints were necessary to get through metric, and then you focus on the intercepts, thereby releasing the factor means in the alternative group. So it's one stage at a time. Okay, does that answer all the questions in the chat window? I think I've caught up. Those of you who are typing. I think so. If not, let me know. Other questions on homework 6 or revisions to homework 5? Any of that stuff you want to talk about? No? Okay. All outstanding work needs to be done by the end of finals week. So if you're not caught up, now is a great time to get caught up because I will turn in whatever grade you have earned at the end of the semester. I think most folks are caught up, and so you should be just fine. Let me know if you need advice on how to revise your homework or if you get stuck on any of these things. All right, then if there's no questions, I wanted to start by telling you that I screwed something up. I know, right? Last time you realized that I was imperfect. I had forgotten to post the slides all together, and I realized as I was going through them, and a question that one of you asked, that I had screwed up one of my examples. So I fixed it, and I have posted a new version of the slides with the fix. And so I wanted to call attention to my mistake to make sure that none of you carry this mistake forward. So it was slide 15 right here. I had this example of covariances between two of the three, and I had said that this was equal to this one. That is incorrect. Why I think I did that is because I started with this middle one and then I tried to come up with like a corresponding example for this one up here and didn't think closely enough. But what I realized is that all three of these combinations on the top are over-identified. All three of them have 1 degree of freedom where one of the direct relationships is not being estimated. So x1 and y2 in all three of these pictures do not have a direct relationship, meaning there's 1 degree of freedom left. But what these three models say is not the same. These two on the left are equivalent. Each of these predicts a relationship between x1 and y2 that goes through y1. So you could multiply the coefficient that is estimated for each of these regression paths together, and that would be what the model says the correlation between x1 and y2 would be. The variance shows up in here if you're dealing with the regressions, but if you talk about correlations, it gets simplified. In contrast, over here on the right, this model says that x1 and y2 are independent because you can't trace through two different covariances the way that you can trace through two different regression paths. That breaks the tracing rules. So this is a different model that says x1 and y2 are unrelated. The models on the left say that x1 and y2 are related, but only because of their shared relationship with y1. And the rest of the slide, I think, is correct. So I apologize for that, but I would rather correct it than send you off into the world with something that I know to be wrong. All right, any questions on that point? Then what we have to do today is talk about actual SEM. So in the SEM example that I built for you, I built it off of real data in a previous analysis that I had published, but I added 2 twists because of what people commonly want to do in structural equation models is test mediation as well as moderation. So I wanted to show you how to do those things. So I have just a couple slides to go over to talk about mediation as a background in case you haven't seen this before. So we went through these things last time and algebra and stuff like that, effect size, and this is, I think, was where we left off. So in path modeling, not all of the variables have to be normal. It says the new slides is not updated on the course webpage. It should be. Well, I will fix that after class. You might have to refresh, but if it's still not working, then I will fix it after class and make sure. But I know I uploaded it because I did that yesterday. So that's the only thing I changed is just that one slide. So in terms of path analysis, you are allowed to include, as long as your software supports it, outcomes of any kind. You can predict binary outcomes, you can predict ordinal outcomes, you can predict nominal, you can predict counts, you can do whatever. The only question is how to do that and what type of estimator to use. And SEM in M+ is the most flexible that I know of. The second that I know of that in terms of offering things is Stata's GSEM package. It has a bunch of different link functions for predicting different kinds of outcomes. It has a less robust treatment of missing data though. So I have some slides here that are just sort of for informational purposes about what you can and can't do in all of these different packages with respect to non-normal outcomes. So Stata, for instance, has a whole bunch of choices, but it doesn't have full information maximum likelihood given these non-normal outcomes. So I have just some stuff on there for your background, and this is what I wanted to talk about today. So, how many of you have seen stuff about mediation before in your courses? Okay, several thumbs, nods. Okay, so then I don't have to belabor most of this. Mediation is the idea of looking at whether or not the effect of a predictor on an outcome has changed after controlling for something else. To me, mediation is nothing more than regression with a better marketing campaign associated with it to make it cooler. And it has new terminology and new things to care about, but it's not that much more than unique effects. Where mediation gets tricky is in dealing with latent variables. So I wanted to show you how you would test mediation type hypotheses in the context of an SEM with latent variables. But this is the basic sort of story. Mediation is the idea that X leads to M, and these are the letters that people always use, so I'm sticking with them, and M in turn leads to Y. And so part of the story here is that X and Y would be related either differently or not at all after you factor in the contribution of M. Common misconception is mediation and moderation. These are not the same. These are not synonyms. The idea of moderation would be shown in a picture like this. My husband, if he saw this, would yell at me, "Not a model!" He hates it when people take path diagrams and do conventions with them like this. What this model actually implies is a model that is down here. So in saying that the M box predicts the line between X and Y, what they're actually saying is that there is an interaction between X and M in predicting Y. So you would have to make a new box. Moderation is something that you can examine in any kind of model. It doesn't have to be a path analysis. I do it all the time in longitudinal, in just regular old regression. You can do moderation, and it involves making a new slope for two predictors or even three predictors that are multiplied together to create that interaction term. And that's all well and good, but what if you want to test moderation of a latent variable? Then you need to make an interaction term that's a circle, and that is trickier. So I want to show you how to do that in the example as well. Some language in terms of mediation effects. People typically label these things as A is the path from the X predictor to the M mediator, B is the path from the mediator to Y, and then C is the path from the predictor to the outcome. And the question is C that you have before controlling for the mediator different than the C that you have afterwards? And so this is C prime to denote that these are not going to be the same coefficient. And it works out that in cases of observed variables and all assuming multivariate normality and stuff like that, that the test of whether C is statistically different than this C prime is equivalent to the test of the indirect effect, which is A multiplied by B. So this result is commonly used as a way to assess mediation. To what extent is the A times B product, the product of those two correlations or regression paths, significant in and of itself? And if it is, then you would draw the conclusion that the relationship between X and Y differs after controlling for M than it does before. So there are a few things about this. It used to be that people would do this in sort of a stepwise fashion. There's an article from 1986 that is sort of the Bible on the topic that has been cited like 40,000 times that describes how to do this as a series of regression models. One of the things that people have argued about since then, and I think has become more standard practice, is the rule as to whether or not C had to be a relationship in the first place. It doesn't. It is still technically acceptable to look for mediation even in circumstances in which the predictor and the outcome are unrelated bivariately, because mediation concerns whether or not the relationship is different, not whether it becomes non-significant, just different. So it could start out 0 and become negative, it could start out 0 and become positive, it could do whatever. So the only rule that I think is still enforceable is this first path. If the predictor does not relate to the mediator, then looking at whether or not there's mediation doesn't make a lot of sense. People have worried a whole lot about how to test the significance of the indirect effect. Um, Here's some stuff about that. I have tried to care about this and I just can't. I'll just tell you that right now. I don't have room in my head to care. There's all this literature on different ways to get a p-value for the indirect effect, and there's like 17 kinds of bootstrapping that people have tried, and I just don't care. I'm sorry. I've tried and I can't. So this is all here in case reviewer 3 yells at you for testing your indirect effect in not the preferred way that they want to. Um, when I've looked at these sorts of relationships in real data, I have found the p-value differs in like the third decimal point. I have too many things to care about and I can't make room for this one. But so I will show you how to get a test of the indirect effect, which is known as either the Sobel test or Sobel. I've heard it both ways. That is given to you directly in M+ using the delta method to get standard errors. And someone may tell you that that's not good enough and that you need to use bootstrapping. But bootstrapping is not always available for every kind of mediation model. So there may be some more research you'll have to do about that if reviewer 3 argues with you. I can help you track that down at some point. But I can show you just the basics of how to test mediation, which is easiest to do in a path analysis or SEM framework in which you can get all the paths simultaneously rather than a stepwise regression kind of path. Question. Would this be when you would argue that it's not game over if the correlation between the predictors and outcomes are not that strong? Yes, I would argue that. In my discipline, some people throw out an idea solely because the first bivariate correlation they look at are super low. It is usually the case that if a pair of variables are not related bivariately, that they won't be related after controlling for other stuff, but there are exceptions to that. And so, yeah, there is the idea that you have to have two variables be related as a gatekeeper to including that predictor in a model is not strictly correct. You could have suppression, in which the unique effect is actually stronger than the bivariate effect in certain combinations of correlations between predictors with outcomes. So yeah, it's not a gatekeeping type of situation. Might be a stupid question. What even is bootstrapping? Oh, not a stupid question. I probably should have said that, huh? Bootstrapping is a resampling technique in which you draw from your sample with replacement another sample of the same size. And you do that over and over and over and over again. And in each sample, you calculate or you estimate the results of your model. And so then you'd get 1,000 different versions of the A effect and 1,000 different versions of the B effect. And in each of those replicated samples, you would figure out what the indirect effect is. Then you have an empirical version of the distribution of these things that you can use to get a standard error. So way back in intro statistics, some of you who had me remember this, what does a standard error tell you? You guys remember the definition of a standard error? Because this is one of those things that I learned it and then it was gone. And then it wasn't until I started teaching this stuff and doing simulation research that it came back. What is a standard error? I've sort of taken it for granted this semester that we know what that is. No one wants to play. They're like, it's the last day of class, Lisa. You're lucky I'm even here. I'm not answering any questions. I'm done. Population mean, yeah, how far off the sample statistic is from the true population statistic. On average, yes, ding, ding, ding. The standard error is meant to approximate how inconsistent that statistic would be across repeated samples of the same kind. So if you did the same study over and over and over again, you get a factor loading in each study. How variable would that factor loading be across studies? The standard error is supposed to tell you the standard deviation of that sampling distribution. How far off on average the sample version of the statistic would be from the true population value. A standard error conveys wiggliness. Back in observed variable land regression, when you're using just regular old least squares to do estimation, the standard errors all come out as ready formulas. Like someone has figured out how to use the data you have to find this quantity. In these models, they're using likelihood estimation. Standard errors are a byproduct of the second derivative of each parameter with respect to the likelihood function. So they sort of fall out as an index of how steep the likelihood function is, where the standard error is 1 over the steepness or 1 over its squared, something like that. So they show up. But in the case of an indirect effect, when you have one variable that's supposed to have a normal distribution, so a sampling distribution in this case, say for A, times a normal sampling distribution for the B parameter, the product of that can't be normal. And so the idea that you could make a significance test by, okay, 2 standard errors around it on this side and 2 standard errors around it on that side is not going to work to the extent that the sampling distribution for the A times B indirect effect is non-normal. So bootstrapping is a way to get a standard error that is based on only like that data. And so you can end up with whatever shape distribution. And so you would just go in and be like, okay, where's 2.5% of the distribution on this side and where's 2.5 on that side? And that's going to be my boundaries for my confidence intervals and stuff like that. So bootstrapping is used whenever you don't trust or don't have a way to compute a standard error for something. And an indirect effect falls into that category. It's also used to get standard errors when you do quantile regression. There's variants of it that are used for other types of statistics. It's used whenever you don't trust the standard error formula or you don't have one. Great question. I forget some stuff that may or may not have been covered in previous courses that I'm assuming. Does that help? So bootstrapping can give you standard errors that are more robust to violations of assumptions, I would say. In M+ and in Stata, they are an option you can just add to any package. For most models, you can say, give me the bootstrap standard errors, and it's like, okay, and it takes a split second longer. It's not available with all combinations, though. Like you can't do it with multi-level models. You can't do it with certain kinds of latent variable models. So for those cases, you may have to do something else if you're bound and determined to get a bootstrap version of your standard error. What I say I don't care about is that in practice, I have seen that the standard errors that are supposed to be incorrect are so close to the ones that you have to get extra work to get that it's not worth the effort. That's what I have seen. But in case reviewer 3 wants to argue about it, I want you to have something to go off of. So indirect effects are something that we tend not to just trust the p-values that show up on the output. At least not everybody. That's what I was going to say. Okay.
I have a question about mediation.
Please.
If you go back to the slide 26, the terminology and regression versus when you call it mediation, is that because of people using it in a causal way, to understand the relationship between the variables?
Yes. People really want to talk about these paths as causal, and you can't do that unless you have a design that supports that interpretation.
Okay. So outside of trying to make a causal interpretation, people would normally just use the regression language?
Oh, no. You will see people do cross-sectional research where everything is a measured variable. There's no intervention, there's no manipulation, there's no random assignment, and they will start talking in sort of causal language because you have these indirect effects. And there is a lot of literature on that suggesting that when you only have cross-sectional data that you cannot get a good estimate of a causal effect because by definition, it takes time for these things to play out.
Yeah.
So yeah, the whole thing is it's squishy. It's very it's one of those areas in which I think people really want to like claim that like it's stronger and more causally interpretable than it is, and the language behind this allows that to seep into result sections in a way that would otherwise get smacked down. So what
T
I
was like nodding, like, I've seen it.
they do. It's like, oh, I have a mediator. Like, well, you controlled for it. Like that's and I know that's not as cool, but that's what it is. So yeah, I you can say you have a significant indirect effect. You can say that the effect of how X relates to Y is significantly different after you control for M. You can, I mean, that's just regression language. I don't think to me, it's not a big deal to say that this indirect path is significant because you could end up with different combinations where A matters but B doesn't, or B matters but A doesn't, and the product is significant. And then it's like, well, how do you talk about that as one idea when you're lumping two things together? So some of this is my bias that I just, I don't care. But so many people have questions about mediators that I want you to have this in your toolbox as a way to estimate indirect effects. What you do with it from there is then, up to the three people who are reading your paper. Actually, two nowadays. I'm an associate editor at Multivariate Behavioral Research, and we are asked to get two reviews. So I am the third in many cases. All right, other questions? Okay, so all this mediation stuff works great until you try to put something that's not normal in the middle of it. So like if you have a categorical predictor that's the mediator, how the hell do you estimate that? It's tricky. So this is where I would encourage you to look at the documentation of your program to see exactly what it's doing. But for instance, let's say that I have a binary mediator. So I have X going into M that's binary. That needs a logit, right? So I would have to have the logit predict the logit of the mediator from X. Well, if I have mediator then as the predictor, which is binary on some Y, that's just a binary variable. That's just a dummy code. So then the A path is in logits and the B path is in regulars. Identity link, I think, would be the name of that. And so then how do you talk about an indirect effect that's on two different scales at the same time? So it's trickier. It's not impossible, but it's a lot trickier if your mediator requires some kind of link function in the middle. So there are references on that that I can help you find if you're in that position. All right, so that was the path model section of the program. There's nothing really new when it comes to putting all of these principles in practice to do an SEM. So just a few slides on that, and then we'll look at the example. Structural equation models consist of two parts. There's the measurement model and there's the structural model. So you have a measurement model set of options for how your continuous latent traits predict your indicator responses. If you pretend that your indicator responses are continuous and normally distributed, then that's CFA. If you allow them to be binary, ordinal, nominal, that's IRT or IFA. And then I don't know what you would call it, but you can have indicators that follow other distributions like counts and stuff like that. So then the structural model is just the process of taking those multiple latent traits and deciding how you want them to relate to each other. Do you want them just to correlate? Do you want them to be indicators of a higher order factor? Do you have other predictors or outcomes that you want to incorporate, such as covariates? Do you need to covary for age or gender or SES or things like that? So all of those sorts of decisions for the structural model follow the same sets of guidelines, rules, principles, and strategies that you learned in just figuring out how to set up regression models. The order of how it goes is based on your theory. It's based on the questions that you want to know. And there's a lot fewer degrees of freedom at the structural level, usually, so there's less room to mess that up. So if an SEM fits badly, odds are good it's the measurement model, it's not the structural model. And so all of the things here that I'm recommending in terms of strategies, make sure that each set of indicators fits its latent factor first. And then when you put it all together, there will be fewer possible reasons for misfit. If it doesn't fit well at that point, it's because of how indicators relate across factors. And then that will narrow down where you can look to see what could be done or should be done to make the model fit better. One thing, when you are doing adding in observed variables within M+, there is no class statement. So that means, say, if you have a 5-group predictor variable that you need to control for, you get to make the dummy codes yourself. You get to do all of the heavy lifting with respect to creating composite joint tests. It wouldn't be F, it would be chi-square in this context for their contribution and all that kind of stuff. In Stata 16, I think they have added the I dot language to their SEM packages so that you don't have to, but just know that ahead of time, that if you need to control for group, you'll have to make the dummy codes yourself. Yeah, there are all kinds of rules that you will see in textbooks about whether or not an SEM is identified. Just look at it. It's kind of the same process by which I decide whether or not a sentence is grammatically correct or you need a comma. It's like I can't articulate the rules, but I know when they're broken. If you look at your model, and this is why I highly advocate starting with the picture, make sure that there's not the same relationship in there twice. So if you have an arrow between two variables, you can't also have a covariance. When you have a higher order factor, for instance, you have to take out the covariances of the lower order factor because the role of the higher order factor is to predict those covariances. So things like that. Make sure that each factor is identified, and then you can troubleshoot non-identification at the structural level on a case-by-case basis. One thing, and this actually just came up this morning when I was helping a student, if the variables that are going into your model are on really, really different scales, it can blow up for that reason. So I had a student who had one variable that had a variance of like 500, and the other variables in the model had variances of 1, and it kept saying it wouldn't go, wasn't identified. And I'm like, okay, divide by 10, fixed. So be careful with the scales. It seems particularly bad in M+, but I haven't had a chance to play with other programs as much. So if your variables are on very different scales, you may need to change their scale so that they're more commensurate so that it will be easier to estimate the full model. In terms of fit, different SEM packages actually incorporate different rules for what counts towards fit and misfit at the structural level. This is another check your documentation to see what it's doing. These are the rules in M+. So any variable that is in the likelihood, meaning it is actually an outcome or you asked it to estimate a mean variance or covariance for it to force it into the likelihood so you can have missing data, any variable in the likelihood, its covariances with the other variables in the model count. So if you don't put in a relationship, it will count against you in terms of fit. If you have predictors that are not in the likelihood, covariances of them with the outcomes that are in the likelihood also count against you in terms of fit. So if you have 4 covariates and you have them predict only some of the outcomes, any of those paths that should have been there count against you in terms of fit. If you miss a relationship between a predictor and an outcome, then that will cause problems. Covariances of predictors that are not in the likelihood do not count for fit. So the covariances among your covariates, for instance, those are not part of the model because they're not in the likelihood and they don't count against you for fit. So I think the rules, from what I understand, not all packages implement them the same way, but these are the rules in M+. So it really depends on how the variable is being treated, whether or not you need to worry about all of its relationships or only some of them. If it's not in the likelihood, then you don't have to worry about its covariance with the other predictors, just with the things that are outcomes. All right, so sequential, we've talked about this a lot. And then that's the what to do if it doesn't work section, which we may not get to, but that's okay. So do you want to see how to do this? The finale. And then you'll believe me that it's really, you already know how to do SEM. There's nothing that much new about this. All right, no, there we go. So this is example 9. This is a new version of example 9 relative to what I have done in my previous classes. And so I dropped some stuff out of here that I had talked about before, and I added some new stuff. So I have a link to what it was before if you're interested in learning about plausible values. But these are real data. They were collected as part of my dissertation. So the focus of my dissertation was examining risk for accidents in older adults and predictors of risk in terms of their visual acuity, their visual attention, processing speed, and the outcome was performance in a driving simulator for which I had 6 observed indicators. So the research that I'm talking about was published in these 2 places. The model that I'm showing you is not exactly what was published. I added some stuff so that it would make a better example, but it is based on real data. So in terms of the code, I am in CFA land for this example. So I am treating all of the variables as if they were normally distributed. I am going to use robust maximum likelihood to provide some degree of protection against non-normality in terms of the standard errors and the fit statistics. So I have a bunch of variables in my data set. I am going to show you a series of models, measurement models first and then a structural model. So the use variables section would be updated for each of the subsequent models that I'm going to show you. I have my missing data indicator. By the way, this right here, M plus allows you to write an equal sign, the word is or the word are interchangeably. And so I thought I had caught this in almost all spots, but I had is there because I used to type things out sometimes. So you may see that in other people's examples, the word is. It works the same as an equal sign. I'm asking for descriptive statistics so that I can make sure that my variables are being read incorrectly, modification indices, standardized solution, and local misfit. Tech 4 is to get latent variable correlations, which we'll use later on. And if I need to save factor scores, which I'm going to do for purposes of illustration, I'm adding this, which I don't think I've shown you before. By default, when you create a factor score file, M+ also includes all of the items that went into the factor score, and it puts an asterisk for missing data, which then makes the data be read in as text when you try to read it into a package. And so you can change that by saying, no, please use a number instead of an asterisk to keep your items as read in as numbers instead of text. So that's just one new option right here. So the process of building my structural equation model, and this is what is reported in the publication, we're going to fit each of the measurement models first and then put them all together because this is exactly what I would do in practice and what I always advocate people do in practice. So first construct is visual impairment. And this construct is going to be indicated by I have 5 different measures of contrast sensitivity. They're lines of different frequencies, and so it's like at what point can you see the differences between the lines? They start to blur together at very high frequencies, as well as a measure of distance acuity. So I'm putting those together to create a latent factor that hopefully measures these older adults' degree of visual impairment. So use variables in this particular model is just those 6 indicators. My latent variable is called vision. I am letting the first indicator here have its factor loading fixed to 1 for identification. And then I have the rest of the indicators here with labels of L2 to L6 so that I can compute an omega down here. So one thing, I don't know if I've mentioned this explicitly. These labels right here, they always apply only to the same physical line of code. So if I had items that wrapped around and I tried to put the label at the end of them, that would not work. So you have to physically label each line of code if you want to be able to use those parameters to do math with later. So this is CFA land, so I've got my loadings and intercepts, I've got in my brackets, I've got my error variances, and I've got my vision factor whose variance is going to be estimated. I am feeding those values into model constraints so that I can compute an omega. And just to make it easier to compute it, I'm calculating the pieces of the omega separately, and I'm including a placeholder for the error covariances, even though there aren't any in this case, just as a point of demonstration. So here are my results. Okay, what is this chi-square test telling me? I have a chi-square of 15.75. What do I do with that information? It's not a trick question, I swear. It's just a review. Good fit, question mark? Yeah. 15 is the rescaled difference between the HO model likelihood and the H1 model likelihood. Which one is mine? The hoe. I am the hoe. You are the hoe. Always remember that, if nothing else from this class. Yeah, so the H1 is the best model. That's as tall as your data can be. M plus does the -2 log likelihood difference corrected for the scaling factors and gives that to you as this chi-square test. The height is not the height is not significantly different from zero close. The difference in height. And that's what the chi-square is testing. It's how far off is my height from the perfect height. And the fact that I have this p-value of 0.07 is telling me that it is not that far off. It is not worse. In other words, it fits. So my 6 indicators, the covariances between them are adequately predicted by the single factor model that I've fit. However, if I look at some of the other indicators, RMSEA is 0.07, confidence interval from 0 to 0.13. That's a pretty big interval, and that's because I only have 152 people. So that's not a lot in this game. But in terms of the other indicators, CFI and TLI, those are telling me how much better my model is than the worst possible null model that has no covariances. They're happy with me. SRMR is 0.04. That's telling me how far off on average in a correlation metric my predicted correlations from the model are from the real ones. So on average, the correlations are only off by 0.04. That's pretty good. So I'm pretty happy with that. Here's the results. So I have a few extra things in here. I computed an omega. So 0.181 would be the reliability coefficient that I would use if I were to create a sum score of these things, which of course I would never do. But that would be what I would give reviewers instead of alpha, because omega is consistent with the model. Another thing that I could report is factor score reliability. So if I wanted to output factor scores and use those as observed variables instead of sum scores, they would be consistent with the model that I fit, but they're not perfect either. So in terms of the estimated factor scores going through this process, the standard error of those factor scores is given here. So there's a formula, which is in your slides, that you can use to compute factor score reliability. Uh-oh. Hey, I'm back. Zoom is like, no, you're not going to compute any reliability on my watch. I'm done. Let me make sure that I'm still recording. Okay, the recording's still happy. All right. There we are. Chat window back open. We're back in business. So it's factor variance over factor variance plus standard error squared. So this would be the reliability that I would report if I were to use these factor scores in a subsequent analysis. It's actually a little bit higher, but it's not perfect. And here are my standardized loadings. These are correlations of
We
each of
can't
the
see the
indicators. Ah! It unshared my screen too. Thank you, T. There. Better? Okay. We can do this. All right, standardized. That's where I was. What do you think of those? I have standardized loadings ranging from 0.57 up to 0.76.
Not the best, but I guess they could be worse.
Exactly. Not the best, but it could be worse. They all relate. So these are in a correlation metric. So I could take these and square them, and that would be the R square for how much of the factor each item's variance is accounted for. So these are, yeah, like nothing's terrible. So on the whole, I have reasonably good fit. All of the indicators are contributing. Reliability is decent. Okay, check. Vision factor holding together well. Here is driving impairment. So I have 6 different measures of driving impairment, which are observed variables computed out of their performance in a very, very low-end driving simulator. I'm trying to remember, to be honest, what they are. It's been, like 20 years. How much variability that they had, like weaving across a lane, that's what lane is. They had to do a divided attention task at the same time where for periodically like a little thing would pop up in their window and they had to either honk the horn or do the turn signal. That was the number of those that they were able to do correctly. How many times they crashed in the simulator. Believe it or not, the high was 19. One of my older adults who drove herself there crashed 19 times in the simulator and then drove herself home. And there's not a damn thing I could do about that. Other than wait to make sure I don't leave until after she's well on her way. But yeah, this was not an intervention. How many stop signs they missed, how many speeding tickets they got on the course, and the total amount of time it took them to complete the course, because some folks decided they would be super duper careful and drive 5 miles an hour through the whole thing. So I wanted that to count against them. So this is a very unconventional kind of latent factor, right? These are observed performance measures, and I'm trying to see to what extent they can indicate someone's ability as a proxy for their real-world driving ability. So I ended up with crashes as the indicator that I picked to be the for identification, estimated all the other loadings, and in previous analyses, I ended up adding a residual covariance in this case. And this is one of the few times that I can say absolutely that this makes sense. So residual covariances are relationships between the indicators in their parts that are not the factor. So a residual covariance is an acknowledgement of unintended multidimensionality. And in this case, it is how the number of speeding tickets that you got is going to be negatively correlated with the amount of time it took you to complete the course. Because if you're not speeding, it takes longer. So the local fit said I needed a negative correlation there, and I'm like, yes, I can defend that one. It's going in. So I did my omega. My residual covariance is going to count against me in the denominator. And I'm noting that I'm dropping 20 cases from this model because out of 152 people, 20 people were unable to complete this task because they got motion sick. Fortunately, no one puked. I was the one doing this whole thing, right? I tested all 152 of these people myself. It was my baby. And yeah, I actually couldn't watch them drive because it made me motion sick as well. But it was very interesting though, because several of them toughed it out. Particularly some of the older men did not want to be seen as like wusses. And one of them like asked for a waste basket and he put it in his lap and he's like, no, I flew airplanes in World War II. I can do this. And he was like, eh. So yeah, but several of them said that they were feeling ill and they didn't want to continue. And I'm like, that's cool, that's cool. Please don't puke in the car. Just, just that's fine. So incomplete data, not missing at random. I did look at that. I couldn't find anything in the data set that related to motion sickness, by the way. That appears to be an unknown reason. So here's my chi-square test of model fit is non-significant. Everything seems, yeah, RMSEA is not bad. CFI and TLI are a little marginal though. They're not great. Let's find out why. So here's my solution. Here's my reliability. Omega is 0.55. There is no universe in which that would be considered good enough. Reliability for the sum scores is 0.73. That's not good either. Here are, let me find where are the standardized results. So here are my standardized slopes. What do you think of these? Well, driving is most related to whether or how many times they crashed. That's the strongest indicator. That seems reasonable. And the others are sort of somewhere between maybe and eh. Like time it took them is actually not related. So this is a great example of great fit, shitty reliability, because they're not the same. A one-factor model is consistent in accurately predicting the patterns of covariance between these two, but they're not that strongly related. And so that could be why the measures of CFI and TLI that want to say how much better it is than the no correlation model are not as happy with it, because there's not a lot of signal to work with here. There's not very strong relationships. But do you know what I did when I found this result? Wrote it up and turned it in because I was going to graduate, damn it. And SEM was going to control for measurement error and fix it. It was going to make it magical and fix it. Then we had one model. This was the contentious model I told you about last week, where I didn't want to have it, but I'm having it today so that I could build an example out of it. I have 3 different measures of visual attention efficiency. Driver scan is D-scan is the one that was the subject for the first half of my dissertation. And here's my happy little model. And I have a question for you. Can you guess why I don't have any fit statistics included in this handout for my 3 indicator model? It isn't testable. Yeah, fit's perfect. It's not under-identified, it's just identified. Yeah, just identified. I have 3 covariances between my 3 indicators, and I've got 3 loadings. So it's going to fit no matter what. The question is, does it make sense? So I can look at the standardized results for that. And actually, yeah, all of the loadings are around 0.7, so this seems like a reasonable thing to throw these 3 into a factor, even if I can't test that their correlations are consistent. I can say that this seems like a reasonable thing to do. So now we're ready for the big finale. And here is my picture. Here's the model that we're going to fit. Dun, dun, dun. So M Plus actually has a diagrammer that it added in recent versions after the creators said they would never ever have a diagrammer. They thought that diagramming encouraged people to be irresponsible and not know what they were doing. And then their lead programmer's 13-year-old son made a diagrammer as a class project. And they were so impressed with it that they put it in M+. So yeah, a 13-year-old wrote the code to do this, which is pretty impressive. So they made the diagram. I tried to make it pretty, but this is the model that we're fitting. So age is a box over here. That's just an observed variable. I don't need to make it latent because I know how old people were. Vision is my latent variable over here, so age predicts vision. Attention is my latent variable over here, so age also predicts attention. I think vision predicts attention. And then I have attention is correlated with processing speed, which is a single indicator measure. Vision predicts processing speed. And then driving is predicted by everything. So my task then is to write the code to fill in all of these relationships between the observed variables and the latent variables. And age is not going to be in the likelihood. I'm treating it as an observed predictor. Processing speed, I am pretending like it's a latent variable to make a point, actually, that I'm assuming that it's perfectly reliable. I'm assuming that the latent version of it is the same thing as the observed, because in the second half of this example, which we're not going to have time for, but I'll make a video about, I can break that assumption. And then I'm also going to fit a latent variable interaction in one of the models between vision and attention in predicting driving. So the code then. The first part of the model is all of the measurement models put together. So all the little snippets of code that I had before at the same time. So I've got my vision model, I've got my driving model, my attention model, and they're all identified so that the factor's variance is being estimated, so it can become factor variance left over, since age is a predictor of all of it. Okay, with me so far? And this is it. The magical word on. So I have age, which I've centered at 75 because all predictors need to have a meaningful 0 point, is predicting the latent factors defined above as vision, attention, processing speed, and driving. And vision is also predicting all of these things. So I've got 4 regressions on the first line, 3 regressions on the second line. Attention is covariated with speed. And then driving is predicted by speed and attention separately. So driving is these are the only 2 things that are predicting it directly. Oh, it's up here too, age and vision. So yeah, everything is that. And so now you can probably guess why I told you that the first thing that I do whenever I look at one of these is to draw the picture. Because once I have the picture, then I can write the code that gets all of these things in the way. So I have latent variables predicting latent variables here, right? Correct. So you can think of this age 75 as an observed X. I've got a mediator of it predicting attention, which predicts driving. So I could see to what extent the relationship between age and driving is because of attention. I've also got age to vision to driving. I've got age to vision to attention to driving. And I've got vision to driving as well. So once you've got your measurement models built, you can use those latent factors however you want, however makes sense, and however fits in with your research questions. So this was my theoretical model of how I thought these things related to each other. Older adults have problems with their vision. Older adults have problems with their attention, but you also can have problems with your attention because you don't have the visual input that's necessary to do the selective attention processing. And it may be the case that people with poor vision did worse in the simulator, or it could be that people with poor vision have difficulties with their attention, and attention is what made them do badly in the simulator. So this is driving impairment is the construct here. So higher scores mean you did worse in the simulator, by the way. So these are all, this is like a map of bad things. So vision is positive, attention is deficits, and driving impairment is this. So yeah, this is what I've got.
Question?
Yeah.
If this is okay at time.
Yeah, please.
So I think this is what you were saying before, but now maybe I understand it differently, like seeing it laid out like this. Is it that the idea is that like you get to a place where you have a good model like this based on your theoretical idea, and then you can use this model to then like look more closely at the different relationships between things versus like before you were saying like you can't, like the idea isn't to, it's not like you're going to fit this model and then like change the relationships between factors and like keep moving factors around and try to like use this as a way to like show what the which relationship is best, correct?
Correct. This is like my theory of how these things relate to each other, and the paths either support my theory or they don't.
And a bad way to use it would be to like switch vision and attention and see if that works better.
Oh, but works better is defined how? In fit?
Supposedly.
Supposedly, yeah. So, if we look at the structural model, is this under-identified, just identified, or over-identified? Are any direct relationships between my 5 constructs missing?
I don't think so.
Nope. It's saturated. So I
Okay.
could I could change where the arrows go. It's going to fit the same.
Gotcha.
I could have driving predict age. That would be silly, but it wouldn't be wrong mathematically. So yeah, if I fit this, this allows me to look at all possible unique effects in the pattern of what leads to what that is logically consistent and answers my research questions. So what I ended up doing, the overall model, which fits well, even though it's significant, meaning that there's probably some cross relationships of indicators or cross factors that I could fuss with if I wanted to. And I have all of the results here. The way that M+ goes through and organizes these, it gives your measurement model results first, so all the by statements come first, then all the ons. So here are all the different regressions where it's y on x. So attention is predicted by vision, was significant. Speed is predicted by vision, was not significant. Driving is not predicted uniquely by vision or speed, but it was predicted by my attention factor, and so on and so forth. Any covariances are given last. And then here are indirect effects that I computed to assess mediation. So let me find that section of the code because I haven't talked about that yet. So these things right here, those are labels. So I labeled my X to M paths. I labeled my M to Y paths. And so then in model constraint, I'm computing 3 different types of indirect effects. Question, the factors here are being predicted by other factors. Those are all considered continuous. Yes. At the level of the structural model, all the latent factors are continuous variables. So it's all just straight up regression, but with latent factors instead. So this here, age viz, is looking at the relationship of age predicting vision as the A path, and then vision predicting driving as the B path. So I'm asking, is the effect of age in predicting driving different after you control for vision? Is the effect of age predicting driving different after you control for speed? And is the effect of age predicting driving different after you control for attention? So the picture actually has 3 different mediational pathways that I could look at here. And in the results, there is evidence that one of them is significant: attention. So age predicts attention, attention predicts driving. So part of the reason why age predicted driving is because of attention. And actually, when you factor attention out, age does not have a significant effect on driving. Yep. These, by the way, these p-values out here, these are the ones that someone's going to yell at you about and say they should have gotten, you should have gotten them via bootstrapping instead. And these are the ones that I've seen not change in practice very much when I do go to the trouble for that. So the model I ended up reporting had 2 paths removed that were non-significant in the previous structural model. The unique effect of age and vision on driving were non-significant, so I took them out and refit the model, and here's the fit, just to make the point that if you're interested in testing whether or not you can leave paths out, the appropriate baseline is the saturated model where you've got everything. So then you can see if leaving paths out is not worse. And so that's the one that ended up going into the paper. What if I wanted to test whether or not the effect of vision depended on attention or the effect of attention depended on vision? Latent variable interaction terms. That's the last thing that I wanted to show you. What I need is an interaction term between 2 circles, because vision and attention are each latent variables. In M+, this is how you do it. So this is what's known as a latent variable interaction. It is not you multiplying anything together. You are asking it to do it. And so I am creating a new latent variable that I'm naming viz attention using this syntax right here. The bar defines new latent variables. We use that in multi-level modeling within M+, and then the magical command xwidth defines the latent variable. And then I put that new interaction term into the model as a predictor of driving. And just because I couldn't go an entire semester without talking about interaction terms and simple slopes, I wanted to show you how to compute simple slopes for your latent variable interaction. So I have slopes for each predictor at high and low values of the other predictor because they've all been mean-centered such that 0 is the middle. And so once you put in a latent variable interaction, this is all the fit you get. It's gone. Latent variable interactions require numeric integration. So there's no more covariance. That's the answer key to come back to. H1 model is gone. So you just have your HO model and your AIC and BIC. And wah wah, my interaction term is not significant in this example. So in practice, I have not been successful in estimating models that have more than one latent interaction at a time. I think it will depend on how much people you have, but this is where it gets to be numerically intensive to do this. So just as a word to the wise. Ta-da! So there you go, mediation and moderation, SEM style. Is it okay if you can add in an interaction without fit because it can't get worse, it can only get not better? Yeah, the fit is going to be largely the same because the interaction term is treated as a predictor that's not in the likelihood. So only its effects on other outcomes would be up for grabs in terms of misfit. So I wouldn't worry about fit if you already know the model fits reasonably well. The worst you could do is need to have the interaction predict everything instead of just driving. All right, so the rest of this, which I'm going to make a video for, which we don't have time for, is what do you do when this breaks? When you try to estimate too many latent variables at a time and you don't have enough people, can I just add shit up and make it into a box and put the box in the model? And the answer is not exactly. So I had the rest of this is demonstrating alternative strategies for reliability corrected factor scores as approximations to the latent variable. But that's it. That's SEM. Once you got your factors, it's up to you to figure out how they relate to each other in a regular old regression model just with circles. The grand finale. All right, questions. When reporting mediation, do people care about total effects and direct effects, or do they just report the indirect effects? It depends. You have to go through extra work if you want to compute the total effects because they're not done for you in latent variable land, but you could go to that trouble if it served your purposes. I don't see what total effects necessarily helps with above and beyond knowing what the direct and indirect effects are. I think those are more useful, but that might just be a personal preference. Other questions? All right, then with the 1 minute that I have left, I want to tell you guys thank you. This semester has not been easy, and I so appreciate the fact that you keep showing up, that you're struggling through this material and fighting through it and getting there and letting me help you. I really appreciate your time, your effort, and being here. If you want to do SEM in your future life, you have all earned the privilege and the right to bother me. By being here, you have a lifetime pass of asking me questions on how to do this stuff. The only thing I ask is that you pay it forward. When someone asks you questions someday on how to do this stuff, you answer their questions, and that's the circle of life. So thank you. Take care of yourselves. Office hours next week if you need anything. Otherwise, have a great break and stay the hell off of Zoom. Bye, everybody.
Thank you.
Thank you.
Thank you.